Welcome, everyone. Just as we get started here, please mute your mics. And as everyone gets situated, we will kick things off in just a minute. As you file in here, feel free to answer the question in the chat or contribute kind of by sharing. But as we dip into the energy session, tell us what energy means to you. A bit of housekeeping today. We have the Q&A section enabled, so feel free to jump in with any questions there or in the chat. As well, when it comes to the Q&A section, really encourage everyone to participate in answering those questions. Myself as well, I'll be in the chat kind of contributing to some of those answers, but we really want to facilitate a group discussion and have everyone engaged. So if you have the answer to someone's question or you think you might have some information to add, we'd love to see everyone's perspectives and get a well-rounded discussion going. Beyond that, if you have any immediate questions for the group, for myself, or for Adam during the presentation, feel free to raise your hand and we'll break it into a part of the flow and try and get that question answered for you. So we're going to jump into things here. Today's webinar session is Energy Fundamentals, Energy Literacy Basics. My name is Alexander Thrower. I'm part of the team delivering this on behalf of Save On Energy, and today I'm joined by Adam Dixon from Know Energy.
Morning.
Our goals of this workshop today is by the end of this workshop, we hope to be able to define basic energy concepts, understand the difference between kilowatts and kilowatt hours, different sources of energy, learn some of the basics of energy efficiency and some conservation tips. And then we hopefully will share with you some free tools and some resources from Save On Energy and beyond that can kind of continue this learning path with you. So to kick things off, we have a little bit of a Mentimeter to get everyone engaged and to get everyone sharing. And here, our goal is we would like you folks to place yourself on this chart about your confidence of discussing energy efficiency or energy concepts.
Yeah, it's it. Yeah, I want to bring up your confidence versus your actual literacy, and I think there is a big difference between the two of them. Because, like, for example, you may know the information, but being able to confident in and communicating it may not always be there. I know when I started out in the energy world, I knew the information, but was not very confident in portraying it outwardly. So just kind of rank yourself how you feel there. Now, Alex, I'm unable to see the Mentimeter poll, so when we think it's been completed, just kind of mention the results to me.
Yeah, absolutely. We have between the two voting polls or between the two options, we're nearing closer and closer to the middle. We started with a far spread from leaning towards high confidence in energy literacy, and now we're moving closer and closer to the middle. So with that, I'm going to turn it over to Adam to give us a little introduction about himself.
So welcome, everybody. So my name is Adam Dixon. I work for a small little company. We're called Know Energy. We work with CIET and Save On Energy to deliver kind of this training and coaching things through Save On Energy. So I've been kind of working full-time in energy since about 2013. And I say I've been working kind of part-time the rest for almost 40 years now. As the company I work for, it's just me and my father. You may have come across some of his training. He does a lot of the Save on Energy training as well. So I've been kind of absorbing little things over the years when I wasn't kind of a resistive teenager to listening to your father. So I've been involved in energy kind of on and off for 40 years and then kind of full time for the last 10, 12 years. And I started off in kind of the residential sector, kind of behind the scenes data management, things like that. And then I've kind of evolved it into more of the training and data analysis sectors now, kind of all encompassing versus kind of more refined back in the day. And as I said earlier, like when I got into this, I say energy literacy is kind of, I'd say, super important. There's a lot of different terms. There's a lot of different things thrown around. I think here in Canada, we're kind of caught between kind of the UK systems and the American systems. So we have a lot of different terms that are thrown around. They don't always make sense and they're not always explained. We hear things like kilowatt hours and we equate them to kilometers per hour. So it's not always as straightforward as you may think. So don't worry if you are not confident in it, or even if you are and you don't understand some of the terms. It's kind of, that's kind of what this is designed for. It's going to bring everybody's literacy basics up to on a higher level. And then also get into some of the more higher level energy efficiency things, but also the high level. I think the high level stuff is just as important as kind of the nitty gritty technical stuff as well. Because if you don't understand the high level, you're not going to efficiently apply the techniques later on. So what is energy? Simply defined, energy is the ability to produce change or do work. That work can be divided into several main tasks that we easily recognize. So there's energy produces light, energy produces heat. So the input of energy produces these things: motion, sound, growth, technology. But at the end of the day, all of that energy, it ends up as heat. That's kind of the law of conservation, the law of thermodynamics. Law of thermodynamics. Energy cannot be created or destroyed. So that's kind of how I like to look at energy, is that all of it ends up as heat. How we look at energy efficiency is how we're going to deal with that heat and manage that heat in our buildings. That's kind of the biggest source of energy. Biggest source of energy and energy efficiency in our buildings is kind of dealing with that heat loss, heat gains in our buildings. Obviously, it's still dealing with the lights. That's not necessarily looked at as heat, so we do want to reduce our load there, but it's all how we deal with that heat. So I had a question around that kind of subject: is what produces more heat, a 15-watt incandescent or a 15-watt LED bulb? And feel free to speak up or type your answer in the chat if you know. Okay. Incandescent, that's kind of what most people would think. It's somewhat of a trick question, is that it doesn't matter what type of light it is, whether it's an LED, halogen, incandescent, anything like that. 15 watts is 15 watts of work. That's 15. That's the same amount of heat. 15 is 15. It's just the difference between the two is how much light you end up getting for that 15 watts. So the incandescent, I'm not saying the incandescent, the LED is more efficient, but the amount of heat produced is still 15 watts of heat. So it's the same at the end of the day. Okay, so moving on. So I mentioned the law of conservation of energy. Energy cannot be created or destroyed, only transformed and transferred. So kind of how this manifests itself into our energy systems is here. So we have oil burns to generate heat, the heat boils the water turns to steam, the steam turns to a turbine turns electric generator produces electricity gets transferred to your homes or your businesses, and then it powers the lights, and the lights give off light and heat in that example there. So kind of one example of the whole energy system. And again, everything ends up as heat at the end of the day. Even at the first step here, the oil burns to generate the heat. There's losses in that system as well. So it's a big kind of balanced system in terms of the higher level picture there. There is other forms of that as well. So energy systems. So there's the fuel getting burned, primary energy, power plant. It's then distributed to the end use there. So it is losses at each step along the way. And actually, to account for some of these losses, if you look at your electricity bill, there is kind of somewhat of a multiplier in there to account for how kind of far away from you are from the primary source of energy is there. So if you're ever wondering, if you're looking at your energy bill and you see 1 kilowatt hours and you see another kilowatt hours and you're billed for the higher one, that is a bit of a true up. It's a simplifying how it works, but a true up to account for those losses throughout the system there. So different forms of energy. There's many different forms. The main two here is the kinetic energy. So this is energy of motion, energy in action, the light from a lamp, the steam from a kettle. The potential energy is energy stored when needed to be released, energy from a battery, cutting wood in your fireplace. So the potential energy in the wood is actually the wood itself. When you burn it, the energy is released. The stored energy released when needed, that can be as simple as if you're going to hammer a nail into wood, the hammer has the potential energy in the mass of that hammer there. So that's kind of potential energy. And then when you swing it, you produce kinetic energy. And then I'll get to kind of the final step of that equation at the end. So kinetic energy can also be thermal energy related to the temperature of an object, total kinetic energy of the particles, radiant energy, electrical energy produced when moving electrical charges. So that's kind of probably the one people are most familiar with. Then we have potential energy. So the chemical energy stored in the bonds between those things. So when they're released, kind of the nuclear energy, and then gravitational energy as well. So the final piece that we're going to put together here is the mechanical energy. And I've tried to as much as possible throughout this webinar to kind of bring in some simpler real world examples as opposed to maybe some of the more complex energy system ones. So mechanical energy is the last one. It's the sum of the kinetic energy as well as the potential energy in a physical system. So I'm going to bring it back to that hammer example. So the hammer itself, that's the potential energy. Then the kinetic energy is the swinging motion, so the motion of it. And then the mechanical energy is when it actually hits the nail, the force that's applied to the nail to force it into the wood. So summing those up, the amount of force that is applied to that nail to drive it into the wood. So now what we're going to do is get into some more of the energy specific terms you may have come across when you're working with energy in your building. So I have a bit of a matrix here, kind of build us up over time to see maybe dispel some of the myths and some of the things and misunderstandings around energy in our buildings. So we have a table here. We're going to have two sides. We're going to build them up together, and then we're going to see how they kind of relate to each other here. So one term you may have heard of, probably everybody has heard of, whether you're built for this at home, you're built for this in your business, so you probably have heard of kilowatt hours. So this is, and is anybody able to tell me, so what is the symbol that is between kilowatt and hours? What function do we apply to those two terms? Kilowatts, which we'll address those, and then hours to get kilowatt hours. Is it division, multiplication, addition, subtraction? Someone feel free to speak up or type in the chat there. This one is oftentimes misunderstood. Multiplication. Yeah, that's exactly right, David. Now, a kilowatt hour. Sometimes people, or not sometimes, oftentimes people say it is division. They equate kilowatt hours to kind of kilometers per hour in your car when you're driving as a speed. It's actually not. It's not that. It's somewhat the opposite of that, but it is multiplied. It's kilowatts times the number of hours that the device or whatever energy system you're looking at is actually using electricity. So
just quickly, Adam, for a bit of housekeeping for everyone, we're not a huge group today, so don't be afraid in these scenarios to unmute yourself if you want. Jump in with a question or a quick answer to Adam, because we're not an overwhelmingly huge group, so feel free to jump in.
So the next one is kilowatts here. So that's actually, I mean, if you're looking at maybe something at home, but you see it being more in watts. So a kilowatt is 1,000 watts. And I'll get into kind of a little bit, which is actually a joule per second. So this is more actually akin to kilometers per hour than the kilowatt hours, even though kind of the wording is a bit confusing, that you may mix those up. So kilowatts, kilowatt hours, kilovolt amps. This is another kind of, I say, maybe more advanced thing that you may come across on your energy bills. It's used to apply to calculate power factor, which we're not actually going to get into in this course here. It's a little bit higher level, not higher level, kind of more advanced level. So don't worry too much about kilovolt amps, which is part of this general, which is kVA. Depending how you're billed in Ontario, you'll probably see kilowatts kVA, and you're maybe billed for which one is higher, because the ISO or your local utility wants to have kind of quality. It's the highest quality electricity. So not quality, wrong word. But I'm not going to get into the details of that right now, just to not confuse people. So if you divide your kilowatts divided by your kVA, this gets your power factor. Power factor is kind of designed to account for, again, another way to account for the losses in the energy system to get it from the generation to your building. So without getting into too much detail, power factor is accounting for the losses in your building. Sorry, a bit of cough. Next thing you may come across is a horsepower. So 1 horsepower equals approximately 746 watts at 100% efficiency. It's 746 watts. If your motor, and it's not going to be 100%, is not efficient, you will see a little bit less of that if you actually to measure it. But 746 watts by definition is 1 horsepower. So back on the right hand side, we have our kilowatts. This is actually our consumption. So this is how much of something we are using. Also referred to as energy. Here, this is demand. So this is the speed at which we need something. Essentially, sometimes I like to explain it as it's the size and the size of the pipe required to get the energy to your building. And if you look at your bill and you're on anything probably above kind of a commercial residential thing, you're going to see a peak demand. You are actually on top of your consumption in kilowatt hours. You are billed for your peak demands because you are influencing the size of the pipe that is required to get that energy to your building. It's also called power. You may come across that term. So the demand. Sorry again. Sorry, electricity and natural gas. This is on the left-hand side. This is, I want someone to fill in the blank. This is how something. And then on the other side, we're going to have how something else. Anybody able to fill in the blanks there? So. While I'm doing that, I'm just going to put in lots and shit. I don't cough anymore. So it's actually, as I've kind of mentioned before, it's how much. And this one, sorry, how fast. And this is how much. So a good way to kind of, again, real world example of this is an analogy I use. And actually, the other day, because people keep talking about AI in the energy world, I just used AI, used ChatGPT to come up with some analogies for some of these things. So kilowatt hour, and a good analogy with this water faucet. So the kW, so kilowatts, is the rate of flow which the water is coming out of your tap. The kilowatt hour is how much water is collected. So if you had a bucket underneath it, it's how much water you collect over a specific time. So kind of another real world example, maybe wrap your head around these things here. Moving on to, and when the price of that is determined kind of somewhat when you use that. So on the kilowatt hours side, so the consumption side or how much side, when you're on a residential, which you may be more familiar with, you have your time of use rates. So you have your on-peak, off-peak, and mid-peak rates. So you have 3 different rates. When you get into the commercial, industrial, Class A, Class B, it's a bit different. But so then it's more tied to your demand, which in your demand, it also does matter when that happens. So there's, without getting into too much detail, depending when it happens, there's the 5 top peaks, they call it. You're billed for your contribution to those 5 top peaks. So the 5 top using days in Ontario, your peak demand, you're billed for that peak demand in there. So again, if you are a Class A, Class B, or a bigger building, we're not going to get into kind of the details of that. There's entire 1-2 day courses on how to understand those bills, so don't worry too much. But I would suggest going out and looking up how to, doing some training on how to understand Class A, Class B billing. So how much times how fast equal, and how long. And oftentimes when energy, the how long, this to me is actually the most important when controlling energy and getting into energy efficiency. Sometimes you can have a massively large load, but if it's not running for a large amount of time, it's not actually going to cost you that much. So how is the consumption kilowatt calculated if my load varies? It's over time, and I will get into that. Long story short, it's the 15-minute average in Ontario. So the load may change over time, but it's actually it's averaged over the 15 minutes. So if you have something that jumps up to 10 kilowatts for 1 minute, but then it cycles back down to that 2 or 3 kilowatt range, you're not billed for the full 15 kilowatts or 10 kilowatts, whatever I said there. It's the average of that over the 15 minutes. So how big times how many? So if you have, let's say, use an example of lighting. So if you have 100-watt LEDs and they're 100 watts and you have 10 of them, that's actually going to be 1 kilowatt demand. So it's 10 times 100, which is 1,000 watts, which is equivalent to 1,000 watts is 1 kilowatt. So we have to multiply by how many. And then kind of jumping over, switching fuels here a little bit. I know we're mainly concentrating on electricity here, but all the energy systems interact. So I think it's quite important to understand natural gas. Natural gas in Ontario, you're billed in meters cubed, so a volume of natural gas. There is in that meter cubed of gas approximately the equivalent to 10.5 equivalent kilowatt hours. And again, don't worry. I know one of the things that intimidates me still to this day is memorizing all of the conversion factors between different fuels. Don't worry too much about it. There's lots of different tools out there nowadays to kind of jump between them, and eventually over time you will memorize those. So then 1 kilowatt hours, another unit you may come across is a BTU, which is a British thermal unit is the acronym there. Again, acronyms are one of the things that still to this day I struggle with. I know BTU, I understand equivalent kilowatt hours, but there's a lot of acronyms. I'd say not just in the energy world, in our world in general today. So BTU, British thermal unit, there's about 3,400 BTUs in 1 kilowatt hour. The next other units you may come across depending on your jurisdiction: joules, kilojoules, megajoules, and maybe the more common is gigajoules. Oftentimes, if you're outside of Ontario, I know in British Columbia, for example, gigajoules is how you see your natural gas on your bill. Now, the next thing is going to go back over to the left side. So we have 1 ton. You may have an air conditioner at your house that is about 3 tons. And that's 1 ton of refrigeration. And that's actually the ton, if you're wondering, that comes all the way back to when we cooled our houses with blocks of ice. So the 1 ton of refrigeration is the amount of the rate of heat transfer. It's not an amount of heat. 1 ton is equal to the heat absorbed in melting 1 ton of ice at 32 degrees Fahrenheit in a 24-hour period. So 1 ton equals 12,000 BTUs per hour. So you could do the math back there that a 1 ton to figure out how many kilowatts your air conditioner in your house is. Oftentimes you'll have your air conditioner, you will see it is rated in tons. So it comes back to an old school thing of actually just melting ice to cool your house. And British thermal units, that's similar. It comes back to a very simple thing here. So approximately 1 BTU is the amount of heat liberated from burning 1 match. So in order to generate 1 kilowatt hour, and this is kind of I like to explain that, like, we oftentimes think of a kilowatt hour as a very small amount of energy or even a very expensive thing for the amount of energy we're getting. We know we talk about the price of energy and the price of energy going up, but to liberate the amount of 1 kilowatt hour of energy, you would have to strike 3,400 matches in 1 hour. And I forget the math on how many that is per second, but I don't think I could do 3,400 of anything in a 1 hour. So maybe take steps, but it's basically you have to swipe all those matches in 1 hour to do 1 kilowatt hour. So it's not necessarily as small of a unit as energy as we think. I know we use a lot of them, and at 10 to 20 cents a kilowatt hour, to me, that kind of maybe justifies the price a little bit there. So calculating power and energy is kind of just another way, depending on how you like to read things. I know that table can sometimes be confusing. Volt amps is volts times amps. Watts is volts times amps times your power factor. Your power factor, as we saw, before is watts divided by voltamps, and kilowatts is watts divided by 1,000. So power factor, again, describes the losses in the energy system, such as electricity distribution system, again. So I think we're quite familiar with that at this point. Energy equals power times time, and kilowatt hours equals kilowatts times hours. And I think, again, the key, if you're going to dive into this, and I would always suggest, if you're looking to explore energy a little bit more, is to look at your house. You can get a lot of data on your utility on your house. You can buy a lot of little things relatively cheap to kind of track energy if you're interested in this. I think I have it sitting here. I might have moved. A little power meter that I bought. I bought a few years ago. It's about $40. I can plug it in to my wall. I can plug my coffee maker into it and kind of measure electricity on it. I have another one. It's a little bit more advanced. It's about the same price, though. It'll actually track the energy over time. I can see the demand, and then I can do that. And there's also kind of the smart plugs and things like that to kind of control those hours. But I think concentrate on the hours if you're going to dive into analyzing any amount of energy in your house. I have a few analogies later to talk about that. So units of energy continued again. I'm not going to spend too much more time on this one. We kind of mentioned horsepower, British thermal units, energy, joules per second. So it's speed. So it's how fast and how much are the keys to that. Kilowatts is how fast. Kilowatt hours is how much. If you're going to take anything out of today, and if you're new to energy or not confident in your energy literacy, I'd say that's something to write down there.
And we just have one question in the chat there, asking us, can power factor be described as another way of knowing the efficiency of a system?
Generally, I'd say somewhat simplification of it, but yes, in the entire energy system from source to kind of sink is your house there. Yes, somewhat, but it was a little bit more complicated than that at the end. So yeah. No, there's no values on the power factor. It's a unitless conversion, unitless number. So now what we're going to get into is going to get a little more detail on energy versus demand. So we've kind of talked about energy. The energy is actually the area under the curve here. So all your consumption, how much is in the bucket of water coming out of the pipe, is anything under the graph here. So I think that's kind of, most people understand that. That's what you see, and that's what you pay at home. That's what you pay in your businesses if you pay the bills. So demand is a little bit different there. So typically it's in kilowatts, as we've mentioned. And then what we want to always look at most of the time is our peak demand. So peak is how the biggest amount of demand we use in the building over one 15-minute period. Yeah, someone said 1 is ideal for power factor, which is correct. I think ideally in a larger building, anything over 0.9 is pretty good. That's kind of what you want to look for in your building. If you're below that, the utility may contact you to do some things to deal with that. So I have a little bit of a problem here. So we're going to go through this and kind of to understand how demand affects your energy bill. So it's not just how much you use, it's how fast you use it, because that's how the system needs to adapt to supply the energy to your building. And you may be hearing a little bit more about that in the news there, about adaptability of the grid as we electrify our buildings and maybe add more chargers for EVs and things like that. As we become more reliant on electricity in Ontario, demand is becoming more and more important there. So understanding the cost and price of electricity. So in January 2005, they used 2,500 kilowatt hours, which equated to $19,670. February, they used only 15 kilowatts more, but their bill went up. I'd say that's about 300 and some odd dollars, $358, I think it is the exact. So energy was actually, so how much was only up 0.01%, but cost was up 1.8%. Why is that? And that equates to more than $24 per kilowatt hour, which is extremely expensive. That's orders of magnitude more than you pay. You pay anywhere from 5 cents to 20 cents on your bill per kilowatt hour. So what happened there? So upon investigation, they used 15 kilowatt hours more at 10 cents a kilowatt hour. So that would equate to about $1.50 extra in that charges. But they had a 60 kilowatt heater that jumped on at a certain point for 15 minutes. So that set their peak demand. So they had 60 kilowatts and they're charged $6 a kilowatt. So it's going back to 2005, this example actually. So it's actually probably a much higher value now. I forget off the top of my head in Ontario, or it depends on your local LDC, but it's a little bit more per kilowatt hour, or sorry, not kilowatt, per kilowatt hour, per kilowatt. So there's $6 here. It's actually closer to 10 probably now. So this problem is even low. It says, yeah, check your local rates. Any numbers I give you here, these things change drastically, so don't necessarily quote them on what your situation. Look up your local numbers. But they should be within range of what you will see. So kind of explain what happened there. Simple demand profile. How fast on the y-axis, how long on the x-axis. And again, we have our kind of a demand profile. Get another term you may have come across in the energy world people use. This is how fast you're using energy over how long. So you're going to see things. We don't need to know the scale on this. This could be daily. This could be weekly. This could be hourly. So kind of things cycling. Maybe this is a 4-day week. They're daily things. And this is our below the curve. Again, is how much per kilowatt hours. And then our fastest peak demand is the highest level over a 15-minute period here. So we can break those down into those kind of 1-hour intervals or 15. This is again the dated example. So this is where that 60 kilowatts, if it is applied at one of those peak periods, it's going to push our peak demand up by 60 kilowatts. If it's actually done in one of these valleys here, kind of a non-issue. You'll pay a little bit extra for the actual how much, but you're not going to pay any more for the how fast there. So being careful of when large loads are coming on in your building is kind of one way to manage the energy in your system. Now, on a residential level or small commercial, this isn't an issue, but when you get into the bigger buildings, this is a major issue, and kind of the majority of your bill is actually on your peak demand. So 15 minutes, 15 kilowatt hours, $1.50. But the new peak is $360, 60 kilowatts at $6 per kilowatt. So that's where we get dinged for that 15, even if it's only on for 15 minutes, that one little heater. So then we have to kind of decide, was that necessary? So hopefully that makes sense to everybody on how to kind of, maybe if you're in a larger building, kind of offset things potentially to make sure you don't shoot up your peak. On the same token, though, that can be used to reduce your bill. So if you know everything kind of starts up at the same time in your building, there may be ways to kind of offset those things. But one of the myths is that startup facilities often sets the peak demand. No, the peak does often also occur midday or at the end of the shift, or not a significant one at all. So you may not have a drastic peak, or it may occur midday. Oftentimes it's tied to the weather. So if the hottest, and typically or historically in Ontario, it's in the summer because we cool with electricity. In the winter, we're a majority heating climate, so we heat with natural gas for the most part right now. So it oftentimes occurs in the middle to later afternoon with the hottest point of the day when our air conditioning systems are working the hardest, and then maybe in an industrial situation, that would definitely almost be the peak demand, because if your process generates a lot of heat and then your air conditioning is working even harder to evacuate all that heat from your building. So it's not always at startup. People think that, although there is opportunities there as well at startup as well. So it says, let the profile speak to you. If you're looking into this, download some sort of data from your utility. Oftentimes you can get utility data, interval data, your 15-minute or hourly data to analyze this. You can plot it on a graph. You can use Excel. There's other tools out there as well to plot that. Let it speak to you, see where your peak demand is hitting, and see if you can do something about that or move that back. Sometimes it may be necessary. We say move it back, don't do it. Sometimes things are necessary in our systems, in our buildings, to keep the building running properly. Again, energy efficiency is never going without something. It's getting it at the best efficiency there. You still want to meet the demands of what anybody needs in the building. So the other myth is that a soft start often saves demand. So a soft start, there's things you can put on, maybe something like a large motor that prevents the inrush current. So oftentimes the current or the kilowatts can be much higher for a few seconds at the startup, even above what the motor is rated for. But because this is only seconds and you're built on 15-minute data, or 15-minute average demand, it's not actually going to influence the demand as much as you may think. It does a little bit because it is a few seconds, but it's seconds over 15 minutes, which is a small percentage of the time. So So another real world example, which uses more energy, goes at like kilowatts versus or demand versus time. So what uses more energy in your house? A clock on the microwave or the actual microwave for cooking? Okay, so but actually oftentimes it's actually the clock that is using more energy over the year than the actual microwave itself. I think you'd have to use the microwave, it's 24, 25 minutes per day to equal the amount of energy that the clock is actually using over time. Depending on the wattages, everyone's different. You may have a microwave that doesn't have a clock, and then this, for example, is irrelevant. So depending on the wattage, you'd have to use it 20, 25 minutes to make up for the clock there, which is about, if something's running continuous, and again, continuous loads are the killers in electricity. So anything that's a continuous load is about $2 per watt per year. So if you have maybe a gaming system in your house, it's got a big sucks of what they call phantom energy. Someone said, just back up, could you elaborate on how the demand meter averages over 15 minutes? Does it take samples every second? I believe, you don't, this isn't, not sure off the top of my head. I believe it takes the average, that's the 15 seconds. Every 15 seconds it's collecting data and it averages that over the 15 minutes. So $2 per watt per year. So if you have, and again, I'm not going to use a specific example of the video game system. In my house, my kind of continuous load, so I look at my evening load overnight. I have a meter also attached to my house, so I can look at this data. Is about 200 watts. So that 200 watts is $2 per watt per year. I'm paying about $400 per year just to run my house at night, for example. So not insignificant. That's probably, if I think about my bills, that's 20% of my bill right there is just from we call continuous load. And I know number of that could probably be turned on and addressed, and you can address some of that with smart plugs, power bars, things like that. I just have this example in there because it happened to be in the picture there of my coffee maker. So energy, cost, and carbon. Kind of once we've moved, we understand our energy, where it's going, how much we're using, we understand our gas. We're also concerned with greenhouse gases, GHGs. There is a carbon tax, or will be some sort of carbon tax on energy in our buildings. So it's worth understanding where the utility cost goes, the energy consumption goes, and where the carbon emissions go as well. So in Ontario, again, general example, this is taken from a real building. This isn't a made up example. Any data I kind of show you here are real world examples here. So utility costs. Right now, electricity far outweighs the cost of gas per unit of energy there. So our costs in our buildings, you're oftentimes going to pay much more for electricity than natural gas, assuming your electricity and natural gas consumptions are equal. So electricity, by this example, is 4 or 5 times more expensive than energy. But when it comes to carbon emissions in Ontario, your natural gas contributes way more to your carbon emissions in your building than your electricity consumption there. So depending on what your goals of your organization, kind of backing up some higher level energy management system, if your goals are to save money, then you need to address your electricity consumption. If your goals are to address carbon emissions, then you need to address the natural gas in your building. So, and there's ways kind of those are the two ends of the spectrum. I say the reality of what you want to do in your building is probably somewhat more in the middle there. And again, if you're diving into this, there's many more training courses than this 1 hour here on energy management that can give you more details on that stuff. Unfortunately, just in an hour here, we're going to touch the surface on a lot of these energy management concepts. So energy and carbon. So this kind of reiterate the point before that your electricity is very low carbon content, natural gas is a much higher carbon content. So understanding these concepts allows you to kind of align what you're doing in your buildings with what your goals are there. So 1 meter cubed of avoided natural gas avoids the emissions of 1.8 kilograms of carbon dioxide. 1 kilowatt hour of avoided electricity consumption avoids about anywhere from 0 to 0.6 in carbon dioxide reduction. And there's a range there because the grid in Ontario, the grid mix is changing kind of constantly there, depending on what's going on in the province there. If we have higher demand, we may need to turn on some of our natural gas fired plants in Ontario, so then the carbon content jumps up a little bit, but it's still very low. That's why in Ontario, the electrification, which you may have heard of, is a kind of a hot topic right now, because that increases your efficiency, as we'll see later, with using things like heat pumps, but it also avoids carbon really rapidly. You can reduce your carbon emissions very quickly with simply electrifying your building. So what is efficiency? Energy efficiency, I've mentioned that a number of times. It's the useful output divided by the input times 100. And the useful part is very important there. That's where the lighting, with lights, if it's a 100-watt light, you pay for 100 watts, but you only get anywhere from 2 to 20% of that as lights. That's the useful part of it to what the function of the device is. The question there, Satwan, well, maybe I'll expand on that in a minute there. So, and again, if you're looking at any of these systems, you may be a bit surprised that compressed air system, that is probably one of the least efficient devices out there. And I think, if I remembering correctly right now, energy in there, you're paying about $4 a kilowatt hour to get energy to your building from a compressed air system. So it's a very inefficient system. So it's oftentimes areas to look in your buildings in order to increase the efficiency. So just make sure I'm on track here. So purchase to end use. Again, these are all the losses in the system. Again, you see everyone has heat. It all ends up as heat. So who would be able to tell me? I've kind of told you what the least efficient device in this tree is earlier with the compressor. Was anybody able to tell me what the most efficient device in this tree is here? So is it the lighting on the work area? Is it the motor to the compressor, which I told you it's not? The compressor is one of the least efficient. Is it a simple electric heater? Is it the lights in the work area? Is it a motor, mechanical, a fan, pump? Yeah, it is the heater. A lot of people talk about electric heaters as being inefficient. They're actually very efficient. They are 100% efficient. You get 100% of the input is put to heat. It's just historically, electric heat is expensive. That's kind of the disconnect that I've seen over the years, is that it's not inefficient, it's very efficient. Electric heat is the most efficient, it's just the most costly in your buildings. And when you get into heat pumps, it's even more efficient. We have greater than 100% efficient heat pumps, much higher. And if that seems weird to you, I'll explain that in a little bit as well. So this is where we're gonna dive. We're going to leave kind of energy basics and understanding kilowatts, kilowatt hours, meters cubed, and then we're going to go to a 3-step approach, to kind of a foolproof approach, I think, to kind of understanding and reducing your energy bills and your carbon footprint as well. So the first step is the first 2 steps, actually. It's waste and efficiency, and then supply. And if that doesn't make sense to you, don't worry. I'll give you some really simple ways to kind of deal with that. So it's number 1 is reduce your waste. Number 2 is increase your efficiency. Number 3 is then deal with the supply. And the reason I do this is that it aligns with full decarbonization or net zero plans, but sometimes more importantly, as you move along through these steps, the cost increases. So if you do the low cost items first, you don't need to purchase as many of the big, higher value items at the end of the day. Some of those items are very cool. I love a nice PV system, but I don't want to buy more than I need. So waste and efficiency. So kind of a matrix here. So eliminating waste. There's a low cost option. There's manual control. Reducing waste is as simple as turning it off. You can manually turn a light switch off. There's a lot of these things have manual controls. Kind of the higher cost is the automatic control, getting into some of the BAS systems, even in your home, those smart plugs, things like that are a little bit more higher cost. Maximize efficiency. So the lower cost is operating conditions. So here, it's good maintenance. You always, your furnace at home, make sure you have a clean furnace filter. Specifically, I mean, not specifically, but more importantly, I'd say even if you have a high efficiency gas furnace, you want to make sure you keep that furnace filter clean. Because as the furnace filter becomes dirty, your furnace will ramp up the demand or the wattage on the motor, and actually to keep the air flowing through it, it will actually use sometimes 3 or 4 times as much energy in that system. So very important maintenance. If you don't have a high efficiency one, your furnace will just run a lot longer to maintain the airflow through there, which also will lead to other maintenance issues and fans and motors and things like that breaking down over time. So the higher cost of this is actually replacing the equipment. But you can oftentimes, in certain situations, using quote unquote older, less efficient equipment if it's run efficiently, is better than new inefficient equipment. So eliminating waste, reduce usage. Step 1, turn it off. Turn it down and then control it. It's pretty simple to me. So fixing leaks, turning lights off, things like that, stuff you don't need, make sure you do that. Turning it down, thermostats, water temperature you may not need at home. Specifically, you may not need your water heater running quite as hot as it is. You may actually not need your thermostat quite as warm or quite as cold as it is in this case. There's lots of information out there about where the human body likes its temperatures to be based on the seasons, and you can actually adjust your thermostat by a few degrees actually, which is about on energy 2 to 3% on heating or cooling energy for every degree you change that. So you can actually adjust it and save significantly on just kind of going with the rules of thumb on what the human body can accept there. So again, if you do like a certain temperature, you may just have to just grit and bear it and say, this is what I'm going to pay for it. Control it. So you can put timers on things, smart plugs, aerators on your water. So even a low flow shower head, low flow taps are very, very important. They save you water, which we don't really discuss because it's not a typical energy, but they also save you on your water heating. So next is maximize efficiency. So again, those operating conditions, change filters, lubrication, controls, things like that. Make sure everything's running how it's supposed to be. And oftentimes when you walk around your house or your building, listen for noises. Noises are one of the #1 indicators of something going wrong in your building. If you're walking through the grocery store, for example, you'll oftentimes hear the compressors on the refrigeration section kind of running on overdrive. You can hear that rattling up in the, whether it's below or above, you can hear a rattling in the refrigeration section in the grocery store. That's probably a compressor or some sort of filter that hasn't been cleaned. And oftentimes, if you take off that grate on the bottom of the refrigerator or the top and you vacuum it out, that can solve a lot of problems with your refrigeration systems in your house or maybe a grocery store, for example. So I always like to do all of these things before I have to go out and buy new equipment. But you can also, on the maximize efficiency, you can go out and buy something. Some things become beyond repair. You maybe need to go buy a new refrigerator, a new furnace, a new air conditioner, things like that. So then we can do optimized supply. This is where we get into that kind of cool, say some not all new and cutting edge, but some of the older cool technologies and some of the more leading edge technologies there. So again, if I have, say, maybe if I have a 30 kilowatt demand in my house, but I can reduce that to 20 kilowatts with turning things off simply, that means I don't need to buy a 30 kilowatt PV array to kind of account for my energy in my building. So I can buy a much smaller system, or kind of maybe more relatable. I did this in my house. And so what I did a bunch of air sealing insulation when I was buying a heat pump. I had a massively oversized natural gas heat pump for a furnace and fireplace. And they were going to put in a heat pump to match that. But I increased the efficiency of my house and I was able to put in a much smaller, much cheaper heat pump at the end of the day. So, and these benefits, they go well beyond energy and carbon. So there's the direct and indirect energy savings. There's also usually with energy efficiency, it's increased comfort, quality, productivity, and safety. An example, in a warehousing situation, we work with a warehouse where we did an LED retrofit to analyze that. And it actually improved the accuracy of the pickers because the quality of the light was so much higher. They were using kind of those old yellow halogen lights. They increased them to LED light, put LED lights in, and the employees were vocal about how much better it was to work in the warehouse, and they were able to pick more accurately, so it increases productivity. And hopefully in that business, there was somewhat of a profit sharing with the employees. So that was tied to that as well. So, and in the real world, kind of people work with this every day, benefits beyond energy. So example is the tires on your car. So you want to make sure those are fully inflated. First of all, it does increase the efficiency of your vehicle. You don't want to burn more gas than you need to, but it also increases the safety. There's a safety element to keeping your tires fully inflated there. So it's not just energy and carbon. There's other issues that come along with the with energy efficiency. So that's historically, I would say way back, it was always like, oh, energy efficiency. You're the guy that's going to come in here and tell me to put a sweater on and freeze in the cold and all that kind of stuff and turn off the lights and work in the dark. No, it's working at a comfortable temperature with the right amount of light, but the most efficient way to get that heat or cooling and light to your space there. So kind of last 10 minutes here, we're going to go into talk about heat pumps a little bit. Heat pumps are kind of hot topic right now. There's lots of incentives out there from different programs to put heat pumps in there. They are a good way to maximize the efficiency in your building. Again, do the first step of eliminating waste, and then go in and put a heat pump. There is some schools of thought that if your goal is carbon reductions, to just jump in there right away and do a heat pump, which will achieve most of those goals. But again, you're going to spend a lot more capital up front to do that. So how a heat pump works. So a heat pump is basically an air conditioner in reverse. So it runs an air conditioner in reverse. So it runs the cold air. Sorry, I'm not explaining it. I'm going to give you a good real world example. So when you spray a can of aerosol like hairspray, if you're a cyclist, you have those CO2 cartridges that you inject into your bike tube, and all that air comes out, the canister is freezing cold. That's the air conditioner part of a heat pump. If you were able to force that air back into that canister, which you can't really do, the temperature would go back up to the temperature it started out at. So it's as things change, expand and contract, they produce hot and cold temperatures. So that's how a heat pump is able to do that. And a heat pump, they oftentimes have efficiencies of, let's say they use a coefficient of performance, which you'll see 2, 3, 4, which is actually akin to a efficiency of 100%, or sorry, 200%, 300%, 400%. And the reason why we can have efficiencies above 100%, which may seem counterintuitive to kind of the laws of thermodynamics, is because we're not converting energy, we're just transferring energy from one mean to another. So for every kilowatt, like COP is for every kilowatt that is driving those compressors and motors, you're able to get 3 kilowatts of cooling in a COP of 3. So you're able to cool it 3 times more than the energy put into it. So, and again, one analogy I've seen recently, and I kind of thought about this over the years, and I found heat pumps a bit weird to understand in your brain, how in Canadian climates a heat pump can work to minus 25 degrees. That's freezing cold to the human body. That's far too cold. So people are like, how does it work? It doesn't work. When I was doing the heat pump in my house, I had contractors telling me, oh, it's going to shut off at a certain temperature. They don't work below 5 degrees, minus 5 degrees, blah, blah, blah. There was a lot of things, a lot of pushback when doing a reno in my home on putting a heat pump in. But you need to think of heat pumps to think about how much heat is in the air. Think about it not in degrees Celsius, not in degrees Fahrenheit. Degrees Celsius, the only reason we use that scale is that's how water reacts to the temperature. 0 degrees C is where water changes phases. In a heat pump, we're using refrigerants where 0 degrees C is irrelevant. So they react at different temperatures, and absolute zero, where there is technically no heat in the system, is actually minus 273 degrees C or 0 degrees Kelvin. So at 300 degrees Kelvin, which is 27 degrees C, which is very warm to most people, and then at 260 degrees C, which is minus 13 degrees, 260 degrees Kelvin, which is minus 13 degrees C, that would feel pretty cold to most people. But there is only actually 15% less heat in that minus 13 degrees C air, because again, it's degrees Kelvin, 300 to 260 degrees Kelvin, that's a 15% change. It's approximately linear, the relationship there, so that's about 15% less energy. So in heat pumps, your efficiency definitely drops when you go to colder temperatures, it does have to work a bit harder. There's no one that's going to say it's going to maintain efficiency, but cold climate heat pumps are able to very efficiently heat our homes down to -25 in our Canadian climate. And the other thing on this is that if you're in maybe the southern Ontario, we don't actually hit -25 as much as people think. The average temperature of the day, we don't actually get that cold. We may get a short period we ever do, and maybe in the northern Ontario portions you may get more, but you want to actually look at your temperatures. And on top of all this, to kind of get on my pedestal here and preach a little bit, is that many other colder climates in the world use heat pumps at a higher rate than we do. Norway, Finland, the Scandinavian countries, I think Norway is 60% of their homes are heated with heat pumps, and that's a colder, I mean, as cold, if not colder than most of our Ontario climates here. So they're a very efficient device. It's just in our context here in North America, they're relatively new. Yeah, someone made a comment about the degrading of the COP. Yes, there is. It does degrade over time. It just means the compressor is working that much harder to recover that much heat. There is less heat, so it has to work that much less hard. And there is a capacity to our systems where you will reach a point where your system will not maintain the temperature in your building, and you either your heat pump will shut off if you don't have a backup system, which hopefully that would never have happened. Hopefully your HVAC contractor thought about this. So usually you will have electric backup, or you will have a natural gas backup here. So in my house, I left in my old furnace. There was reasons, decision making, that I'm doing a renovation in 3 to 5 years, so I didn't want to spend 20 grand right now to have a electric backup and a full heat pump. So I left in my natural gas as my backup one, and I shut off my heat pump. I've done the analysis on the cost to benefit ratio. I shut it off at -12. So definitely does degrade over time. Oops. So here, I mentioned that hybrid heat pump system. So here, this is kind of an example. I think this is actually close to my house here. So this is, I'd say, the most cost-effective way to upgrade your efficiency of your building, spend the least amount of money, and also reduce your carbon emissions here. I think right now, this is kind of the important thing. If your heating and cooling systems are both failing and you have a goal of net zero in your building or carbon reduction, then I maybe go to the full heat pump with electric backup, all that stuff. You're going to almost reduce your emissions, almost be close to net zero immediately there. But if you don't want to do that, like I didn't want to do right now in my building, I can put in a relatively smaller heat pump. So it only supplies me 86% of my capacity, but because its efficiency, it delivers 99.9% of the heat to my space. So I only actually need my electric backup for 0.86% of the time, or 0.86% of my energy. So it's a very small percent of my time. Now, this analysis I did based on shutting my heat pump off at -20. I've adjusted that kind of over the year since I've had it in order to reduce my bills overall as much. So again, in terms of carbon emissions, the difference between those two things. So the air source heat pump with pure electric backup, we have a 93.8% reduction in carbon. But if I do that hybrid system, I still have a 93.1% carbon reduction. So only a difference of 0.7 in carbon reduction. So very, very small. Now, if I was to go net zero in my building, the amount of PV or carbon offsets or things like that you can do to further reduce your carbon, I only need a small amount of those because they're relatively costly. So a couple other benefits of heat pumps, kind of going beyond energy, is if you do a full heat pump, no more fossil fuels in your building, no more risk of carbon monoxide poisoning. Indoor air quality is improved anytime you're burning anything. I know there's been a lot of information come out the last few years, just specifically with natural gas stoves. The air quality in your house can deteriorate. Lower insurance rates. If you don't have a fossil fuel burning, you don't have anything burning, you can potentially have lower insurance rates. Then oftentimes you do have to upgrade your electrical panel to do some of these things, or depending on your situation, but there is other benefits to that. If you have to do it, then you can then anticipate further things down the road on maybe your net zero journey. And then so the carbon reductions we've kind of talked about. And the last thing with mini splits, one of the systems where you have individual room control. So you have those, oftentimes you go to a hotel or maybe some newer homes or homes in Europe and Asia. They have individual heat pumps in each individual room, so you can control this. There, it's very handy. In my in-laws have a house. They have their main floor is done with a central heat pump. Then all the bedrooms upstairs, they have 5 bedrooms. They each have their own little mini split in them. So when we go and stay with them, we can actually control our room compared to my mother-in-law likes it at about 10 degrees C to sleep, and my wife doesn't, so we can keep our room at maybe 17, 18, and they can keep their room at 10 degrees there. So quite handy. So just some more. I wanted to get to some of the kind of resources. I think Alex will touch on kind of more training available to you through the Save on Energy program, post-webinar support. Now, there is one thing I will point out is one-on-one coaching services. So by attending some Save on Energy trainings here, you are entitled to energy coaching. So there is a link there. So the post-webinar support intake form, you will be provided copies of these slides. Also, go there, fill it out. You'll be directed to kind of an expert in that area. It may be me, it may be someone like Alex, just depending on what your question is. You get a couple hours of kind of free training or free coaching from Save on Energy. So survey, I think Alex will post a link to the survey in the chat as well. But the main thing I wanted to get to, I think, is online resources. There's tons of them out there. Heat pump specifically, I've put a link to this specific channel. It's a UK-based company, but I find they explain heat pumps very well and all of this stuff very efficiently in 7-8 minute videos. I know I don't typically like to plug specific companies, but because they're kind of removed from our context here in Ontario, then they're in the UK. I think it's a good resource to kind of learn about heat pumps, where they can go right, where they can go wrong. They go very high level if you're not a technical person, and they dive into the super technical things as well. So it's a very good resource there, as well as many other resources out there if you just Google heat pumps there as well. So I know I crammed that all in there in the last couple minutes, but I think we're at time there, Alex.
Yeah, thanks, Adam. Thank you for setting a really, really solid foundation for us. If you wouldn't mind taking us back to the green slide. Perfect. So as Adam mentioned, and I added a little bit more information in the chat, there's those one-on-one coaching opportunities, and those can range anywhere from kind of personal growth within the energy field to really kind of industrial setting and energy management training and stuff like that. So if that is something that interests you or your organization, please don't hesitate to reach out. You can do so through the post webinar support intake form that you'll see in the slides following this video. But also I added in the chat and here on your screen, there's the training and support at IESO email address. And that's a monitored inbox to really provide all sorts of information related to these training sessions, related to webinars. So please don't hesitate to reach out there. And I encourage everyone to stay in touch with the bulletin because there's plenty more webinars available, such as this one. And again, we have a huge range all the way here from energy literacy basics, all the way up to kind of really industrial courses and information sessions regarding kind of the whole range of energy that's out there. So please don't hesitate to reach out. And as a question was asked at the beginning of this was recorded and will be posted on the Save on Energy website. So you can access it there and it will be shared. Any information will be shared on the Save on Energy website. So thank you to everyone for participating. And if anybody has any questions, Adam and I will be around for another minute or two. But yeah, we appreciate everyone's participation.
Yes, thank you. And have a great weekend, people.
Thank you.
Thank you.